Before we drift into the depths together, take a moment to get comfortable. Adjust your pillow, let your shoulders drop, and allow your breathing to slow. This is Whisper Logic, where we explore the quiet wonders of our world while you ease into rest. Tonight, we're descending into the deep sea, where darkness reigns and life takes on forms you've never imagined. There's no rush here, no urgency, just facts flowing like currents, carrying you deeper into sleep. Let's begin our descent. The ocean's Hadal zone is a place most people will never see, never touch, never truly comprehend. It covers less than 0.2% of the seafloor, such a small fraction. And yet, this narrow slice of the ocean floor spans nearly half of the ocean's entire vertical depth. Imagine that for a moment. Half of the ocean's depth compressed into less than a fraction of its floor. It's a vertical world, not a horizontal one. A world of trenches and canyons that plunge down and down and down. As you descend through the water column, as you move away from the bright surface where sunlight dances and warms, something happens. The water changes. It's not just darker, it's colder. The temperature drops degree by degree, and the water itself seems to thicken around you. It grows heavier, denser. The pressure begins to build, slowly at first, then relentlessly. Every meter you descend adds weight to the water above you. The ocean presses in from all sides. At just a few thousand meters down, something profound occurs. The last traces of surface light vanish completely. It's not a gradual dimming anymore. It's the end. Total darkness. The kind of darkness that land dwellers never truly experience. No moon, no stars, no distant streetlight bleeding through a curtain. Just black, absolute and complete. And in this blackness, life continues. Life adapts. Life finds a way. In the absence of light, the creatures of the deep sea have learned to live differently. They've abandoned the rules that govern life in the sunlit zones above. Many of these creatures rely on senses we barely understand. Chemical sensing, the ability to taste and smell the water around them, to detect the faint molecular trails left by other animals. Vibration sensing, the capacity to feel the tiniest movements in the water, the subtle displacement caused by a fin stroke or current shift. These senses replace what we would rely on. They replace sight. Some animals have gone further. Some have let go of vision entirely. They lack eyes completely. No pupils. No lenses. No photoreceptors waiting for light that will never come. Instead, they navigate by touch, by smell, by the feel of the water moving across specialized organs along their bodies. Imagine living in perpetual darkness and never once feeling lost, never once wishing for light, because you've never known it, because your world is built on different foundations. But not all deep-sea creatures have abandoned sight. Some have evolved vision so specialized, so strange, that it seems almost alien. The Barreleye fish, for instance. This creature has a transparent head. Transparent. You can see right through the dome of its skull to the organs inside, to the tubular eyes that point upward. Always upward. These eyes don't swivel side to side like ours. They stare straight up through that clear shield, watching for faint silhouettes above, watching for the shadow of prey moving between the fish and whatever dim light might filter down from far, far above. It's a patient existence, a waiting existence, eyes fixed on the ceiling of the world. Then there's a cockeyed squid, an animal that seems to have split its vision into two separate jobs. One eye is large, bulging, always looking upward toward the surface. This eye searches for shadows, for the darkest shapes of animals swimming overhead against the faint glow above. The other eye is small, pointing downward into the deeper darkness below. This eye watches for bioluminescence, for the living lights that flash and pulse in the black. 2 eyes, 2 worlds, 2 hunting strategies in one body. It's efficient, practical, strange and beautiful in its asymmetry, because in the deep sea, where sunlight has long since surrendered, bioluminescence becomes something else entirely. It becomes a dominant form of communication and hunting. Living light, chemical reactions inside the bodies of animals, producing photons, creating glow. Blues and greens mostly, colors that travel well through water. Animals flash signals to each other. Warnings, invitations, threats. They use light to find mates in the vast darkness. They use it to startle predators. They use it to lure prey close, so close, and then strike. But some creatures have evolved a trick that gives them an edge. Dragonfish, for example. These sleek predators emit red light. Red, a color that most deep-sea animals cannot see. Their eyes aren't built for it. They've adapted to see blues and greens, the common colors of bioluminescence. But red is invisible to them. So the dragonfish swims through the dark with private spotlight, a beam of red illumination that reveals prey without alerting them. The prey doesn't know it's being watched, doesn't know it's being found. And then it's too late. Stoplight loose jaws take this even further. These fish use multiple wavelengths of light, different colors, different frequencies. They can target specific prey based on what that prey can or cannot see. It's like having a toolbox of flashlights, each one tuned to a different task. Need to see something that hides from green light? Use red. Hunting something else? Switch wavelengths. It's sophisticated, calculated, a reminder that intelligence in the deep sea doesn't always look like intelligence on land. The darkness of the deep ocean is not empty. It's not silent or still. It's full of light that lives, full of creatures that have spent millions of years learning to thrive where we could not survive even minutes. And as you lie here, breathing slowly, letting your body sink into rest, remember that right now, in the deepest parts of the ocean, dragonfish are hunting with invisible light. Barreleye fish are watching upward through transparent heads. Cockeyed squid are splitting their vision between 2 worlds. And all of it happens in darkness. All of it happens in cold and pressure. All of it happens beyond our sight, beneath the weight of an entire ocean, in a world we're only beginning to understand. Let that image settle in your mind. Let the deep sea hold your attention gently, and let yourself drift, slowly, deeper into sleep. In the deep sea, survival often means disappearing, becoming invisible, erasing yourself from the eyes of predators and prey alike. And in a world where bioluminescence lights up the darkness, where flashes and glows betray your presence, invisibility requires ingenuity. It requires tricks that seem almost impossible. Take the cookie cutter shark, a small creature, barely longer than your forearm, drifting through the mid-depths of the ocean. From above, a predator looks down and sees nothing. No silhouette, no shadow. And this is the trick. The cookie-cutter shark glows underneath its body. Light radiates from its belly, matching the faint downwelling light from far above. It erases its own shadow. Counterlumination, scientists call it. The shark becomes invisible not by hiding in darkness, but by mimicking the light around it, by filling in the space where its shadow should be. It's camouflaged through light, and it works perfectly until the shark is close enough to strike, taking its signature circular bite from whatever animal drifted too near. Hatchetfish do something similar. These thin, blade-like fish hover in the twilight zone, their flat bodies angled to reduce their profile. Along their bellies, light organs glow softly, but this isn't light they produce on their own. They house bacteria inside specialized pouches. The bacteria live there, fed and protected, and in return they emit a steady glow. It's a partnership, a symbiosis. The hatchetfish adjusts the brightness of its belly to match the light filtering down from above, tuning the glow with shutters and lenses. Perfect camouflage. The fish vanishes against the background. Certain squid do this too, carrying their own colonies of glowing bacteria, adjusting their light to disappear into the water column. But there's another kind of invisibility in the deep sea, one that doesn't rely on light at all. Many deep-sea animals appear bright red, vivid crimson, scarlet, the kind of red that would stand out dramatically in shallow water. But down here, in the darkness, red light doesn't exist. Remember the dragonfish with their private red spotlight? Most animals can't produce red light. And without red light, red pigment reflects nothing. It absorbs what little blue and green light might reach it, and it appears black, pure black, invisible. So these red shrimp, red jellyfish, red squid, they drift through the deep like ghosts, hidden by color alone. Some creatures take transparency to an extreme. Glass squid and certain jellyfish have bodies that are nearly transparent. You can see right through them, or almost through them. Their tissues diffuse light rather than blocking it. Light passes through, scatters gently, and emerges on the other side without creating a hard outline, without casting a shadow. It's not perfect invisibility, but it's close. Close enough that a predator might look right through them, might not register their presence until it's too late or until they've already drifted past. But transparency has a problem. Organs aren't transparent. Stomachs full of food aren't transparent. A glass squid might have a clear body, but if its stomach is visible, if the dark content shows through, the whole disguise fails. So some creatures have evolved solutions. They hide their dark stomachs with shields, mirrored layers that reflect light, scattering it so the stomach doesn't create a dark spot, or black gut shields that absorb light completely, creating a small darkness that somehow doesn't register to predators the same way an entire body would. It's problem-solving at the cellular level. Evolution finding workarounds for the limitations of transparency. Then there are the comb jellies, ctenophores. These gelatinous animals shimmer as they move, their bodies flashing with rainbow colors. But it's not bioluminescence. It's not pigment. It's their cilia, tiny hair-like structures arranged in rows along their bodies, beating in waves to propel them through the water. These cilia bend light. They diffract it, splitting white light into its component colors the way a prism does, the way a soap bubble does. The comb jelly shimmers blue, green, violet, red, all in sequence as the cilia beat. It's beautiful, mesmerizing, and it serves no purpose for camouflage or communication that we know of. It's simply a consequence of how they move, a side effect of their biology, beauty for its own sake, flickering in the deep. And now, let's talk about pressure, because everything in the deep sea happens under weight. Tremendous, crushing weight. At the surface, the atmosphere presses down on us with a force of about 14.5 pounds per square inch. We don't notice it. We're built for it. But as you descend into the ocean, every 10 meters adds another atmosphere pressure. At 100 meters, you're under 10 atmospheres. At 1,000 meters, 100 atmospheres. And in the deepest trenches, the Hadal zone we spoke of earlier, pressure exceeds 1,000 times atmospheric pressure at the surface. 1,000 times. 16,000 pounds per square inch. The weight of an entire ocean pressing in from every direction. For most life on Earth, this pressure is fatal. Instantly, cells would rupture, proteins would collapse, air spaces would compress to nothing. But trench animals have adapted. Some trench fish live their entire lives at these depths, and they cannot survive decompression. If you brought them to the surface, they would die. Not from lack of pressure support, exactly, but from chemistry. Their proteins, the molecular machines that run every process in their cells, are built to function under extreme pressure. The pressure stabilizes their shape. Without it, near the surface, these proteins begin to unfold, to unravel. The fish's biology simply stops working. It's like taking a machine built for one environment and forcing it into another. The parts don't fit anymore. Amphipods, those small crustaceans that scuttle through trench sediments, use a different strategy. They incorporate special molecules into their cells. Pressure-loving molecules. Piezolites, scientists call them. These small organic compounds nestle into cell membranes and between proteins, stabilizing structures that would otherwise deform under pressure. They're like molecular braces, holding everything in place. With these molecules, amphipods can thrive where most life would fail. They've chemically adapted to a world of crushing weight. Gelatinous animals are perhaps the simplest solution. They avoid rigid skeletons entirely. No bones, no hard shells, nothing that would shatter or crack under pressure. Their bodies are mostly water, and water doesn't compress. It's effectively incompressible. So a jellyfish, a salp, a gelatinous zooplankton, these creatures feel the pressure, but it doesn't harm them. It passes through them. They are soft, flexible, built from the same substance that surrounds them. In a way, they barely distinguish between their bodies and the ocean itself. Pressure shapes life in the deep sea as profoundly as darkness does. It determines what forms are possible, what strategies work, what creatures can descend, and which must stay above. And as you lie here, your own body under nothing more than the gentle pressure of blankets and air, consider those animals living under 1,000 atmospheres. Consider the cookie-cutter sharks glowing to erase their shadows. The glass squid diffusing light through transparent bodies. The comb jelly shimmering with rainbow cilia. The amphipods braced with special molecules. All of them adapted. All of them thriving. All of them living in a world so different from ours that it might as well be another planet. Let these images blur together now. Let them soften. The glowing sharks, the transparent squid, the pressure-loving creatures of the trenches. Let them drift through your mind like bioluminescence through dark water. And let yourself sink deeper, deeper into rest, deeper into sleep, down where the pressure is gentle, and the weight is only the weight of your own body, relaxing completely. Life in the deep sea moves slowly. It has to, because down here, energy is precious, food is scarce, and every movement, every heartbeat, every thought costs something that might not be easily replaced. So deep-sea creatures have evolved not just to survive the pressure and the darkness, but to exist on almost nothing, to live at the edge of what's possible, metabolically speaking. At the cellular level, everything is reinforced. Enzymes, the proteins that catalyze chemical reactions, are built with extra bonds extra structure to keep them stable under pressure. Ribosomes, the molecular machines that build new proteins, are fortified with additional components. Cell membranes, which would normally become rigid and brittle under cold and pressure, are enriched with special lipids that keep them flexible. Even muscles are chemically reinforced, their fibers adapted to contract and relax in conditions that would immobilize shallow water animals. Every system, every molecule, bears the mark of adaptation. Nothing is left to chance. Everything is engineered by millions of years of evolution to function in the extreme, but reinforcement alone isn't enough. These animals must also conserve. The snailfish, which holds a record for the deepest living fish ever recorded, maintains an ultra-slow metabolism. Its cells operate at a fraction of the speed of surface-dwelling fish. It uses minimal oxygen. Its heart beats slowly. Its muscles contract lazily. It doesn't rush. There's no need to rush. Food doesn't appear suddenly in the trenches. Prey doesn't dot past in schools. Everything happens slowly down there, and the snailfish has matched its pace to its environment. Slow and steady, efficient, built to survive on scraps. Hatchetfish, those thin blade-like fish we talked about earlier, have mastered the art of stillness. They hover motionless in the water column, their bodies angled just so, barely moving at all. To hover like this requires almost no energy. They are neutrally buoyant, suspended between sinking and rising, and they hold that position for hours, days, even, waiting, conserving every calorie. In food-poor waters, movement is expensive, so they don't move unless they must. They wait for food to drift to them, for prey to pass within striking distance. Patience becomes survival. And then there's the bony-eared assfish. Yes, that's its real name. This deep-sea fish holds a peculiar distinction. It has the smallest brain-to-body ratio among vertebrates. The smallest. Its brain is tiny relative to its size, almost absurdly so. And this isn't a defect. It's an adaptation. Brains are expensive. They consume enormous amounts of energy relative to their size. Neurons fire constantly, processing information, maintaining awareness. For an animal living in a featureless, unchanging environment where complex thought provides little advantage, a large brain is a liability. So the bony-eared assfish is scaled back, simplified. It retains just enough brain to handle basic functions. Swim, eat, reproduce, and nothing more. It's brutal efficiency, neural minimalism. Some animals conserve energy through buoyancy. The deep stereo jellyfish, a bizarre sheet-like creature that looks more like a floating garbage bag than a living animal, drifts effortlessly through the deep. It doesn't swim. It doesn't propel itself. It simply floats, neutrally buoyant, carried by currents. Its body is so thin, so diffuse, that it offers almost no resistance to the water. It just exists, suspended, waiting for small prey to brush against its tentacles. No effort, no expenditure, just patient drifting through the dark. Cirrate octopuses, sometimes called Dumbo octopuses for the ear-like fins on their heads, have also abandoned the high-energy lifestyle of their shallow water relatives. Most octopuses use jet propulsion, sucking water into their mantle and blasting it out to shoot backward. It's fast, it's effective, but it's exhausting. Cirrate octopuses flap gently instead, using those ear-like fins to pull themselves through the water in slow, graceful movements. They look like they are flying, floating. It's mesmerizing to watch, and it uses a fraction of the energy that jetting would require. They've traded speed for endurance, urgency for sustainability. But where does the food come from? In a place where photosynthesis is impossible, where there are no plants, no primary producers creating energy from sunlight, what sustains these ecosystems? The answer falls from above. Marine snow, a constant, gentle rain of organic matter drifting down from the sunlit zones thousands of meters overhead. Dead cells, fecal pellets, molted exoskeletons, mucus strands, the waste and debris of life near the surface, sinking slowly, aggregating into larger clumps as it descends. It looks like snow in the water, hence the name. Soft white flakes tumbling down through the darkness. And this marine snow feeds entire ecosystems. It's the foundation of life in the deep. Some animals have evolved specifically to harvest this drifting bounty. The vampire squid, despite its ominous name, is not a predator. It doesn't hunt. Instead, it drifts through the water trailing long filaments, sticky threads that catch particles of marine snow. When the filaments are coated with debris, the squid pulls them in and scrapes the organic matter into its mouth. It's a passive strategy. Patient. The vampire squid is a filter feeder of sorts, collecting the falling snow and extracting whatever nutrition it can. In an environment where chasing prey would expend too much energy, this approach makes perfect sense. Sea cucumbers take a different approach. They settle on the seafloor, those vast abyssal plains covered in fine sediment, and they vacuum. Literally, they extend feeding tentacles or mouths and suck up the sediment, processing it through their guts, extracting whatever nutrients might be trapped among the particles. Bacteria, organic fragments, microscopic remnants of marine snow that settled and mixed with the mud. They are the janitors of the deep sea, cleaning the seafloor particle by particle, turning over sediments that might otherwise lie undisturbed for centuries. Giant amphipods, those oversized cousins of the tiny beach hoppers you might find on the shoreline, have developed an even more sophisticated approach. They eat the organic matter that reaches the seafloor, but they can't digest it alone. It's too complex, too degraded. So they house gut bacteria, entire colonies of microorganisms living inside their digestive systems. These bacteria ferment the organic matter, breaking it down into simpler compounds the amphipods can absorb. It's a partnership. The amphipods provide a safe home and a steady supply of food particles. The bacteria provide digestion services that would otherwise be impossible. Together, they extract energy from debris that would seem to have no energy left to give. This is how life persists in the deep sea, through reinforcement, through patience, through partnerships and simplifications and strategies that minimize cost. The snailfish with its slow metabolism, the bony-eared ass fish with its minimal brain, the jellyfish drifting on currents, the octopus flapping gently instead of jetting, the vampire squid collecting snow on filaments, the sea cucumbers vacuuming sediments, the amphipods fermenting matter with bacterial help, all of them living on the edge, extracting maximum benefit from minimum resources, thriving in a place that seems too harsh to support life at all. And yet they thrive, slowly, quietly, without urgency. And as you lie here, breathing slowly, your own metabolism settling into rest, let yourself mirror these creatures. Conserve. Slow down. Let your thoughts drift like marine snow through darkness. Let your body become as still as a hatchetfish hovering in deep water. There's no need to rush. No need to think hard or move or plan. Just drift. Just float. Just let the gentle current of sleep carry you deeper, deeper, into the quiet dark where nothing urgent happens, where everything moves slowly, where rest is a natural state, and let yourself finally, completely relax. The deep sea is full of specialists, animals so adapted to their specific niche, their specific strategy, that they seem almost purpose-built. Strange forms that make perfect sense once you understand the problems they're solving, the challenges they face. And nowhere is this more apparent than in how these creatures find and consume food in an environment where meals are rare and unpredictable. Consider the acorn worm, a simple creature, elongated and soft-bodied, burrowing through seafloor sediments that might be thousands of years old. These sediments hold carbon, ancient carbon, locked away in mud particles that settled long ago, carrying with them the remnants of life from the surface. Most animals couldn't access this carbon. It's too old, too degraded, too tightly bound to mineral particles. But acorn worms have digestive systems capable of breaking these bonds, of extracting and recycling carbon that has been locked away for generations. They are time travelers in a sense, consuming the ancient past, releasing nutrients back into the ecosystem, turning the old into the new, the buried into the available. Other animals have evolved bodies shaped entirely around the act of feeding. The gulper eel, for instance. This creature has a mouth so disproportionately large compared to its body that it seems almost comical. The mouth can expand like a net, opening impossibly wide, ballooning outward to engulf volumes of water many times the size of the eel's head. It swims through areas where small crustaceans and jellyfish drift, mouth agape, collecting everything in its path like a living plankton net. The prey is filtered from the water, and the water is expelled through the gills. It's inefficient in the sense that the eel captures a lot of water for relatively little food, but in the deep sea, where prey is scattered and sparse, casting a wide net is sometimes the only strategy that works. The pelican eel uses a similar body plan but adds deception to its arsenal. Its mouth, too, is enormous, capable of expanding to grotesque proportions. But at the tip of its long, whip-like tail, the pelican eel carries a bioluminescent organ, a glowing lure. It dangles this light in the darkness, waving it gently, attracting smaller fish and invertebrates that mistake the glow for prey or for a mate. When something approaches, curious or hungry or confused, the pelican eel strikes. Its massive mouth engulfs the victim before it realizes the mistake. The light was a trap, a beacon leading not to food or companionship, but to death. Then there are predators whose entire skull is a weapon. The goblin shark, with its elongated snout and protrusible jaws, looks like something from a nightmare. Its jaws aren't fixed to its skull the way yours are. They are mounted on elastic ligaments that allow them to shoot forward, launching out of the shark's mouth like a spring-loaded trap. The shark detects prey using electrical sensors in its snout, drifts close without alarming its target, and then snap. The jaws shoot forward, grab the prey, and retract back into the mouth, all in a fraction of a second. It's a slingshot mechanism, precise and devastating, allowing the shark to strike from a position that seems too far away to be threatening. Viperfish and lizardfish are ambush specialists. They don't chase. They don't patrol. They simply wait. Their bodies are built for stillness, dark coloration, minimal movement. They hang in the water column or rest on the seafloor, virtually invisible, and they wait for prey to wander too close. When it does, they explode into motion. Their mouths, filled with needle-like teeth, snap shut on the unfortunate victim. The strike is over in an instant, and then the fish returns to stillness. Back to waiting. They can go days, weeks even, between meals. Patience is their greatest asset. Stillness their best disguise. Snipe eels have taken a different approach. Their bodies are absurdly long and thin, almost thread-like, and their jaws curve outward in delicate arcs lined with tiny teeth. They coil through the water like living fishing lines, their bodies forming loose loops and spirals. When prey drifts near, the snipe eel doesn't lunge. It doesn't close the distance aggressively. Instead, it strikes from wherever its jaw happens to be in that coil configuration, snagging the prey from a distance and drawing it in. The entire body is a trap, spread through space, waiting for contact. Some deep-sea fish have abandoned swimming altogether in favor of standing. The tripod fish plants itself on the seafloor using 3 elongated fins, 2 pelvic fins and the lower lobe of its tail fin, that extend like stilts. It stands there, perfectly still, facing into the current. Its other fins are spread wide, covered in sensors that detect vibrations in the water. When a small crustacean or worm drifts past, the tripod fish feels a disturbance. It knows exactly where the prey is without seeing it, without chasing it. It simply adjusts its position, opens its mouth, and the current carries the prey directly in. It's a passive strategy made possible by standing still and letting the ocean do the work. Other seafloor dwellers have learned to walk. Batfish and goosefish use their pectoral fins like arms, modified into limb-like appendages that let them crawl across the bottom. They move slowly, deliberately, their fins gripping and releasing the sediment with each step. It looks strange, almost terrestrial, these fish walking along the seafloor as if they are halfway to becoming land animals. But it works. Walking uses less energy than swimming when you're moving short distances. And on the bare and abyssal plains, where there's nowhere to hide and nothing to chase, slow methodical movement is enough. Dumbo octopuses hover above the trenches like ghosts. Their ear-like fins flap gently, holding them suspended just above the seafloor, drifting over the sediments in search of worms and crustaceans. They don't hunt aggressively. They don't need to. They simply drift and watch, and when they spot something edible, they descend, wrap their arms around it, and move on. It's graceful, effortless. The Dumbo octopus embodies the patience and efficiency that defines deep-sea life. And then there's the big-fin squid, one of the strangest animals ever captured on camera. Its arms and tentacles are impossibly long, sometimes exceeding 20 feet, trailing behind and below its small body like the strings of a living kite. These appendages are held in odd angles, forming shapes that resemble elbows or right angles, and they trail through the darkness as the squid drifts. Scientists believe these arms are sticky, coated with mucus or lined with suckers, and that the squid simply drifts through the water, letting its arms trail behind, catching whatever small prey happens to contact them. It's a bizarre strategy, alien and unsettling, but it works in an environment where active hunting would expend too much energy. Each of these animals has found a way. The acorn worm recycling ancient carbon, the gulper eel expanding its mouth like a net, the pelican eel with its glowing lure, the goblin shark with its spring-loaded jaws, the viper fish waiting in stillness, the snipe eel coiling like a fishing line, the tripod fish standing on elongated fins, the batfish walking with arm-like appendages, the Dumbo octopus hovering gracefully, the big-fin squid trailing impossibly long arms through darkness. All of them specialists, all of them perfectly adapted to problems we can barely imagine. And as you drift here, in your own darkness, in your own stillness, let yourself be like these creatures, patient, efficient, not fighting or striving, but simply existing, allowing solutions to come to you rather than chasing them. Let your body settle like a tripod fish on the seafloor. Let your thoughts trail like the arms of a big-finned squid, loose and disconnected. Let yourself hover like a Dumbo octopus, suspended between waking and sleep, drifting gently downward. There's no need to hunt for sleep. It will come to you. It will drift close, and you will simply accept it, easily, naturally, without effort. Let go now. Let the deep sea hold you, and rest. Life in the deep sea exists at every scale. Not just the fish and squid and jellyfish we've been exploring, but smaller, much smaller, down to the microscopic, down to the invisible foundations that support everything else. Microbial mats coat surfaces in the deepest trenches. These are colonies of bacteria and archaea, single-celled organisms so small that millions could fit on the head of a pin. They form living carpets across trench walls, stabilizing sediments that would otherwise slump and slide. They cling to rock faces, to organic debris, to anything solid, and they recycle nutrients, breaking down complex molecules, converting chemicals from one form to another, creating food for slightly larger organisms, which in turn feed larger ones still. These microbes are the foundation, the invisible layer that makes everything else possible. Without them, the deep-sea food web would collapse. The trenches would be sterile, but they persist, quietly doing the work that allows life to continue. Foraminifera, single-cell protists that build intricate shells from calcium carbonate, blanket the seafloor in living carpets. They are everywhere, and countable. When they die, their shells accumulate, layer upon layer, forming the sediments themselves. Much of the deep seafloor is made from the remains of foraminifera, centuries of death compressed into stone. But the living ones continue, feeding on bacteria and organic particles, reproducing, dying, adding their shells to the growing layers beneath them. They are so numerous that they form entire ecosystems unto themselves, microhabitats where even smaller creatures live among the forests of their shells. But the deep sea is not untouched. We like to think of it as pristine, as a last wilderness, but that's not quite true anymore. Pollutants like PCBs, industrial chemicals banned decades ago, are found even in trench animals, in the tissues of amphipods pulled from the deepest points on Earth, in the bodies of fish that have never seen sunlight. Ocean currents carry human chemicals to the planet's deepest places. Plastic particles drift down with the marine snow. Microfibers from synthetic clothing. Fragments of bottles and bags, broken down but never truly disappearing. They settle into the trenches. They are consumed by animals that mistake them for food. Even here, even in the most remote and inaccessible part of the planet, our presence is felt. It's a sobering thought. That untouched silence, that darkness we imagine as pristine, bears our distant imprint. The deep sea is connected to the surface, to us, by currents and chemistry, by the slow rain of particles carrying not just nutrients but contaminants. And yet life persists, quietly, adapting where it can, suffering where it cannot, but persisting. In total darkness, where no human eye can witness, where no light has ever naturally reached, life continues its ancient routines. The gulper eel expands its mouth. The tripod fish stands on the current. The Dumbo octopus drifts above the trenches. The anglerfish waits with her fused mate. The tube worms absorb nutrients from their bacteria. Every movement is deliberate. Every calorie is precious. Nothing is wasted. Nothing is rushed. The deep sea operates on a principle of absolute efficiency because anything less would be fatal. The deep sea is not ruled by monsters. That's a human projection, a fear of the unknown. The creatures there are not malevolent. They are not waiting to attack or destroy. They are simply living, doing what they've evolved to do, hunting when they must, hiding when they can, reproducing when the opportunity arises. They are ruled by patience, balance, and time, by the slow accumulation of adaptations over millions of years, by the careful management of energy in an environment where waste means death. Far below the surface, where the pressure is crushing and the cold is absolute, evolution whispers instead of shouts. Changes happen slowly, gradually, a slightly more efficient enzyme here, a marginally better sensory organ there, small improvements compounding over vast stretches of time. There are no sudden revolutions, no dramatic leaps, just steady, incremental refinement. The deep sea rewards patience above all else. Reward the organisms that can wait, that can endure, that can make do with almost nothing and still survive. And there's something profound in that, something worth considering as you lie here in your own darkness. The deep sea teaches us that survival doesn't require aggression or speed or dominance. It requires adaptation, efficiency, the ability to exist with minimal resources, the patience to wait for what you need rather than frantically searching for it, the wisdom to conserve rather than expend, the microbial mat stabilizing trench walls, the foraminifera blanketing the seafloor, the pollutants drifting down from a world that seems so distant, the life persisting despite everything, the deliberate movements, the precious calories, the patience and balance in time, the whispered evolution happening grain by grain, generation by generation, across centuries and millennia. Let these images settle in your mind now, not as exciting facts to remember, but as a feeling, a sense of the deep sea's rhythm. Slow, patient, enduring. Let yourself adopt that rhythm. Let your breathing match the pace of deep sea life. Slow, so slow. Let your thoughts drift like foraminifera settling to the seafloor. Let your body become as still as a viperfish waiting in darkness. There's no need to move, no need to think, no need to do anything at all except exist, quietly, patiently, in your own deep darkness. The deep sea persists, life persists, and you can persist too, in this moment, in this stillness, simply being, simply breathing, simply sinking deeper into rest. Let the weight of sleep press down gently, like the weight of an ocean. Let it surround you, support you, and let yourself finally release into it completely. The deep sea holds its creatures without effort, and sleep will hold you the same way, effortlessly, completely. Just let go. Let the darkness be complete, and rest.